In this problem, we're asked to find which rectangle with a given perimeter has the largest area. So to solve this, we should first think, what kind of problem is it? As we're told to find the thing with the largest area, this is a optimization problem. But we're given extra information. We're not just finding which rectangle has the largest area, because that would be potentially infinite. We're given a constraint that the rectangle must have perimeter P. So we notice that this problem is a constrained optimization problem, one where the objective to be optimized is area, and one where the constraint is perimeter. So a useful place to start would be to draw a picture. So let's give ourselves a rectangle, and let's label the sides. We don't exactly know which they are, so when you don't know something, you should give it a name. So let's label this side length x and this side of length y. So now a reasonable thing to do would be to formulate this problem precisely in terms of x and y. So that is to say, we want to find the minimum of area, but area is x times y, subject to a constraint and that constraint is that the perimeter is P. So the perimeter is 2 times x, 1 from the bottom and the top, plus 2 times y. So this is such that 2x plus 2y equals P. Now, we hopefully remember that if we have a constrained optimization problem, we should consider using the tool of Lagrange multipliers. And the first step in using Lagrange multipliers is to formulate the augmented function that is to be minimized. And the first step in doing that is to write the constraint in the form g of xy equals 0. So this equation we need to put in the form g of xy equals 0. And so for that to work, that must mean that g of xy is equal to 2x plus 2y minus p. And we'll label this objective xy as f of xy. So the first step of the Lagrange multiplier technique is to form the augmented function h, which is a function of x, y, and the Lagrange multiplier, which is usually called lambda, and this is equal to the objective minus lambda times the constraint. So it's very important that the constraint equals 0 in order for this to work. So in our case, we know what f and g are, and so in this case, this is h of xy is equal to xy minus 2x plus 2y minus p, and there should be a lambda in here. The point of Lagrange multipliers was to take a constrained optimization problem and turn it into an unconstrained one. That's exactly what we have now. Now, in order to solve this problem, we find the unconstrained maximum of h. So we've reduced this problem to find the minimum of h, but now h is a function of x, y, and lambda. But this is a much simpler problem. In order to find the minimum of a function over all values of x, y, and lambda, we need to simply set the derivative of h with respect to all of those variables to be 0. So the next step to do is to set the gradient of h with respect to x, y, and lambda equal to 0. We're now ready to do the computation to find the minimum of h. So let's give ourselves a new page. We're after the minimum of h equals xy minus lambda times 2x plus 2y minus p over all x, y, and lambda. That is to say, this is an unconstrained minimization problem. The solution to this is given by the critical points of x, which are the points such that dx of h is equal to 0, dy of h is equal to 0, and d lambda of h is equal to 0. So let's compute dx of h, dy of h, and d lambda of h. So the partial derivative of h with respect to x gives us a y from this term and a minus 2 lambda from that term. So we get y minus 2 lambda. The partial derivative with respect to y similarly is x minus 2 lambda. And the partial derivative of h with respect to lambda gives us minus and this whole function g. So this is minus 2x plus 2y minus p. And for these to all be part of the minimum of h, these must all be 0. We then have three equations with three unknowns, x, y, and lambda. We can combine the first two to say y equals 2 lambda, x equals 2 lambda, and so hence x equals y. But if x equals y, we can combine that with the third equation to say that 4x minus p equals 0, which is to say x is equal to p over 4, and y is equal to p over 4. So what we've shown is that the rectangle of perimeter P with the largest area is such that x equals y equals p over 4. So it's a square. Strictly speaking, we haven't shown that this is a minimum. We've only shown that it's a critical point. But in this case, we can reason geometrically that of all the rectangles of perimeter P, this must be a maximum